All right, I think we're ready to go. Welcome to day 13 of assembly language class. Today is going to be a good day. Sorry, that came off a little bit loud. Today's going to be a good day because there are some tricks that we have avoided using up to this point, and it's going to be awfully nice to have them. Really early in the semester, we looked at a number of addressing modes, ways of accessing the operands that our machine instructions can use, but we've really gotten by with just 3 of them so far. We've left out 4 more that we're going to see today. I know that sounds like a lot, but all 4 of them are really closely related, and they really just look like different syntax for the same kind of thing or different levels of complexity. So far, we've depended on addressing modes that use direct addressing, where I guess the operand could be in a machine register. One of the operands could be immediate data, or if it was in memory, we always told the assembler exactly where we wanted it in memory, or at least what offset within, say, our data segment. We didn't have a good way of, like, if you had a variable in memory, we didn't have a good way of looking around at nearby memory locations. But today we're going to learn the addressing modes for doing that kind of thing. This will let us implement things like arrays of bytes or arrays of words, or even arrays of what we would call structs in a language like C, where every element of the array could be a little object that we want to index into. To do this, we're going to have to learn a handful of indirect addressing modes. These are ways where, well, typically we get the address of memory that we want to access by, or at least we get the processor to get it through the contents of 1 or more registers. Usually, this will involve, if we're using more than 1 register, we might be asking the processor to access memory by adding together the value of a couple of registers or a couple of registers in a constant and using that as an index into one of the segments. Other processors might let us do more sophisticated things. And I'm really talking about this green section of the slide here. So typically we compute the absolute address of what we want to access, or at least we get the processor to do that by adding up the contents of multiple registers. But if we were trying to index into an array where every element was, 20 bytes in size, then doing that would also require some multiplication. Some processors have that built in. On the 8086, we'll have to do any more sophisticated indexing. We'll have to do that ourselves. So we'll be asking the processor to access memory based on what we might call an index, or if you're coming from C, something that we're already accustomed to calling a pointer. We know where a memory location is, or we know where it's stored that we want to access, and we just need to get the processor to do that. Let's take an example that shows the kind of thing we might want to do, but we can't do a very good job of it yet. Let's say we had a whole bunch of values, like a list of values that we wanted to add up. And that's what I'm making over there on the left. You can see we're pretending that's in the data section of our program, the data segment. And I just made a bunch of word-sized variables, A, B, C, all the way up to D. If we wanted to add all of those up, given what we know, we could access any one of them. Let's say we wanted to add up all of those and store the sum in AX. We could do that. It just wouldn't be, we can't do it a very good way yet. Sorry about that sentence. We don't have good techniques for doing this. Over on the right, that's how we could do it. I copy a 0, so I clear out the AX register, and then I just go through each of the variables one at a time, taking what's in that variable and adding it to AX. And if I've got 26 variables like this, that'll take 26 lines of code. But you can see this doesn't generalize very well to a really big array, or I guess cases where I don't know how big the array needs to be. If these are values that I don't know about till execution starts, then this technique isn't going to work for being able to add them up. Um, so we want to be able to get the processor to compute a location in memory to access data items we want to work with. Now, there is a way to do this, even with just the indexing modes and the instructions we have right now. And for some instruction sets, this is or at least for some approaches, this is a legitimate way to do what we're going to end up doing. This is just not how we're going to do it. Imagine we had an instruction like that, add whatever is in A to AX. Now, if you look at what this assembles down to, it's kind of like the sequence of bytes there in the middle of the slide. The add to AX assembles down to part of an instruction, and then the A part becomes the address or the index into the data segment for some variable A. So it's going to be, typically we'd write it in hexadecimal, but it's the location of where A is. So that instruction assembles down to something like this add to AX, some particular offset. So that address of A kind of becomes like immediate data in that instruction. If we knew where that address was or where that part of the immediate data was, we could write an assembly language program that changed its own code, and that could let us use that same instruction to access any location in memory. Like if we ran this instruction and then we went in and modified this part of the instruction, modified these red bytes in the program's code, and then reran the instruction, and then did that again, changed this location and reran the instruction, we could trick that same instruction into reading from different locations in memory. For some approaches, that's a legitimate way to go. I guess it has the disadvantage that if you had two programs running the same instruction at the same time, or if you ran it and then you came back and ran it again, you'd have to worry about the state of that instruction when you actually executed it. So modifying your code as a program is running can create some problems. Fortunately, we've got other ways of trying to do this, and we'll describe these by an example. Let's pretend you've got a list of items. And when we say list, we kind of mean an array of items, one item after another in memory, all of them the same size. In the data section, it's easy to make memory for a list like this. You've seen, at least in the readings, this dupe syntax that lets you specify what a particular part of the data section should look like. Here we're saying, I want you to be able to put a 0 in the data section, not just once, but I want you to put 10 of those in a row. And the DW out here says these are all word size. So that directive says to the assembler, reserve a section of the data segment that looks like this, that starts out full of word-sized zeros. And then let's pretend we've got a piece of code that goes in and fills them in with some other value. There we were just reserving space, so let's pretend maybe we read a bunch of values from the user. And we want to just, kind of like we were saying in our earlier example, we just want to add up all of these values. Here's some pseudocode for what we can pretend we want to do. I just want to loop for 10 iterations since I've got 10 values. If this was an array in a higher level language, I could just index off of the name of that array to get any one of these items and just add up the value that's there. In assembly language, in 8086 assembly, the way we're going to be able to do this is by using registers to keep up with really different parts of this high-level language syntax. Let me try and say that again better. We're going to write code in assembly that does the same thing as this. So it'll have a loop counter. It will be looking through elements of the array. We're just going to have to use CPU registers to do that. So we'll use the CX register to keep up with the iteration we're on. So it'll count up from 0 up to 9. And then when we hit 10, we know we're done. We will use AX to keep up with the sum. So it'll kind of be doing the same job as the sum variable we're pretending we have here. And we'll use SI kind of like a pointer that's going to move through each element of this array, looking at what's contained in each element, looking at each of those words of memory. Now, we're using SI. I don't know if we've used it much, but you'll remember in addition to AX, BX, CX, and DX, we've got some other registers that some of them are used for special things, like the stack pointer is used for keeping up with where you are on the stack. The base pointer is also used to keep up with typically a location on the stack that doesn't have to be the same thing as the stack pointer. And there are these two index registers, source index and destination index. And you can do different things with them, but they're normally used for indexing through, for looking through different segments of memory, or I guess for keeping up with a location and then moving around from that location. So we're going to use SI kind of like a pointer to one of these elements as we go through this array. So what's it take to code this? Well, first part's easy. We'll clear, so we're going to use AX to accumulate the sum. So we'll clear that. We'll copy a 0 into the 16-bit AX. And if CX is like our variable I, if it's counting iterations in the loop, we'll also start it out at 0. And if SI is going to be like our pointer, then we'll make it start out holding the address of this first value. And then as we go through the values, we'll move it ahead to hold the address of each successive value. We've used this syntax, I think we've used this syntax before. Yeah, when we've passed strings to the function call or the system call for printing out strings. Sometimes we just needed to get the address of a thing in memory. Well, list, we're pretending that's our, yeah, like we're declaring it over here. That's the name for the starting location of this list of words in memory. If we said list with square brackets in it, we'd be asking for the contents of that first word size thing. But if we say offset list, that gives us the location in the data segment of this list variable that we created. So you can think of that as evaluating to at least the assembler. When we say offset list, it gives us a pointer to the first address on that list, the memory address that list assembles down to. All right, so that's kind of the first part of this loop. We got a pointer to the first item. And then over and over, we're going to try to add up an item. And this is our first indirect addressing mode. It looks kind of, it looks kind of like syntax we've used before. I want to add something to AX. Normally, when we put something inside square brackets, it's the name of a variable. It's something in our data segment. But here I'm using SI, the source index register. And when you put a register inside square brackets like that, you're saying to the processor, go get the memory address in SI. And remember, we just loaded up SI with the address of this first item. So go get whatever SI points to. Go get the memory address in SI, get the contents of that, and copy it into AX. We made this list as a bunch of words, so each of them is 2 bytes. This is going to go get a word out of the memory pointed to by SI, because that's what we said to add to. Since AX is a word-sized register, it'll go get a word of memory starting from address SI, so that one word right there, and it'll add it to AX. Again, the square brackets make it look kind of like a direct addressing mode. But the fact that there's a register in there tells it we want to get the contents of memory at whatever address that register holds. Questions before we try to move on? That instruction right there is really the first example of a new thing we're seeing today. All right, I'm not hearing questions.
I would have assumed.
Oh yeah, question, go ahead.
Yeah, it's just I would have assumed that we would have because this looks like like, can you tell me how this isn't like the self-modifying thing you talked about earlier? I'd
I
assume it would
can.
be.
I
I
don't want to back up. Let me finish talking through this example, and then catch me if I don't talk about it. I'll try and cover it there. Any other questions that I might be willing to take at this point?
Can you only do this with SI and GI, or can you do it with other
Almost.
registers?
There are 4, we'll talk about this later. There are 4 registers that you can use this way. And they're BP, BX, SI, and DI, but that's on a slide later. So there are some restrictions. Other questions? All right, moving on. So this was the interesting part. And then we just got to finish the loop. So after we get one item, we need to move ahead to the next item. And the first thing we're going to do is move the pointer. So here, SI, I'm just adding 2 to it. And that makes sense. Since every word is 2 bytes, it means the start of this word is 2 bytes later than the start of this word. So every time I go from one item to the next, I'm moving 2 bytes ahead. If you're fresh out of the C class, you should notice this, because remember from C, when we do math on pointers, we get a behavior that's usually called pointer arithmetic. If you've got a pointer to a short and you add to it, if you add 1 to it, it moves 2 bytes ahead, because that's how big a short is. Notice that assembly language is not like this. In fact, when we do this add instruction, it doesn't really even know what kind of data SI points to. It's just a register as far as assembly language is concerned. So we have to be smart enough to move it 2 addresses ahead, or to add 2 to it, to get the address of the next thing. Questions? I think that line is probably the second most interesting line here. Here we're this is kind of like the pointer dereference operator. Go give me the contents of memory this points to. And this is like pointer arithmetic. Move the pointer ahead by 2 bytes. And then just to run this loop like it's written, we'll increment the loop counter. And then we just need to see if we've hit 10 or not. So we can compare CX to 10. And then if it hasn't hit 10, we'll jump back to the top and take another iteration. So that jump if below, once we are equal to 10, that'll bail us, that'll get us out of the loop. We had a question a moment ago that I will address now. So this should be a working solution that uses one of these indirect addressing modes. How is this different from self-modifying code? Well, SI is not the address of a variable. When this instruction assembles down, it assembles to an instruction that says, go get the contents of memory pointed to by SI and copy that word, or add that word to AX. When we add one to SI, we're changing the contents of a register, but we're not changing our own code, which meant if you had, I know I'm assuming if you're in OS class right now, you've talked about threads by this point. If you had 2 threads running self-modifying code at the same time, you might be in trouble, because they might each expect a different version of that code. But here we could do that. 2 threads could be running this code at the same time. They would each have their own contents of SI, so they wouldn't mess with each other. Backing up a whole bunch of slides. This was our example of self-modifying code, and I'm pretending this here, this isn't the list of data we're accessing. This is the machine instruction for that. So we're actually going in and changing that part of the machine instruction just to trick it into reading different memory locations. Whereas, a bunch of slides ahead, what we're doing right here doesn't have to do that. Other questions or any follow-ups on that one? All right, I covered a little bit of this already. If you wanted to connect the dots between assembly language and the C that you're already familiar with, well, a pointer in C could be any of these 4 registers that I just mentioned, ones that can be used in indirect addressing modes, and we'll see the slide that actually lists those in a moment. In C, if you had to get the address of a thing and copy it to a pointer, well, we just saw all we have to do is ask the assembler for an offset of a variable in our data section, and that's like getting its address. And then pointer dereferencing in C is like putting that register, if a register holds a pointer, then putting it inside square brackets is like asking for the thing it points to, or the contents of memory it points to. Backing up a slide, while we've got this example, we can talk a little bit about an instruction that could make this a little bit shorter. We've talked about it before, but we didn't spend much class time on it. I think I mentioned it and we talked about it a little bit, but here we can revisit that. We could make this a little bit shorter using the loop instruction. In fact, this example is kind of made to invite the loop instruction because we're already using CX as our loop counter variable. And you may remember we talked about this at least once. The loop instruction is made for writing counter-based loops, and it's made with the assumption that the loop counter is in CX. It just counts down instead of up. We could simplify this by using that instruction. We would just have to start CX out at the number of iterations we want. And then at the bottom of the loop, so the loop instruction is kind of made for writing loops that count down to 0. And it's made with the assumption, it's made to write a loop that takes at least one iteration. You can use it other ways, but the natural way of using it is kind of what I'm showing here. You can start out CX with your loop counter. And every time you hit the loop instruction, so this is a assembly language instruction, it decrements CX. And as long as CX is not 0, it goes to whatever label you specify. So it's kind of like a conditional jump. It's just it also manipulates the value of CX at the same time. So if you start out the counter CX at 10, every time you hit the loop instruction, it'll decrement it. And as long as it hasn't hit 0, it'll go back to the top. So CX will go down to 9 and then 8. And then on the last iteration, if CX is 1, you'll go all the way down to this loop instruction. It will decrement it. Now it's 0. And once it hits 0, it just flows on through to the next instruction. So it's assuming you start out CX with a positive number, and that's the number of iterations it's going to do. That's why I said it's made for writing loops where the assumption is you're going to take at least one iteration, because based on what I've said, if you started CX out at 0, loop is going to behave, well, predictably, but probably not the way you want. If you start CX out at 0 and you hit this loop instruction, it's going to decrement CX. Well, now CX is not 0 anymore. In fact, it does a decrement as if it's well, doesn't really matter. But you can think of it as treating that variable as an unsigned integer. So when it decrements it, it's not 0 anymore. Now it's maximum value for a word, around 65,000. And then it'll jump back up to the label because it's not 0. And then it'll keep looping and decrementing it. Eventually it'll stop, but it's going to take about 65,000 iterations before it stops if you start out CX at 0. So if you have to write a loop where it might need to take 0 iterations, you can still use the loop instruction. You just have to, and we've got an example of this later, you just have to plan around that behavior. You have to avoid accidentally taking 65,000 iterations. But for what we've got to do here, loop's going to work just fine because we're taking exactly 10 iterations. Here's how we could do it with the loop instruction. And this is the way we just did it. And you can see we saved 2 instructions by doing it this way. Same as before, I'll go through it real fast. We load 0 into AX. We load our pointer into SI, but we start out CX at 10 and we're going to count down. Each time we get an item out of the list and add it to AX, we move the pointer ahead, but we don't have to decrement CX because loop does that for us. We don't have to test it against 0 because loop does that for us. All it really is kind of like a substitution for, or at least all that we're left with is what looks like a substitution for the branch. If you haven't hit 0 yet, jump back up to the top and keep decrementing. So using this instruction, at the time, probably this would let the processor implement this loop faster because there are fewer instructions. And I didn't say this, it's on the previous slide. This uses CX, but it doesn't mess up your condition codes. So if you had something you cared about in the condition code, using loop will test against 0. It just does it without overriding what was in the condition codes. So you could still depend on what value you had left in there. Questions before we try to move on? All right, we've got a problem. It's a problem that we haven't had to worry about yet because we were always copying stuff from our data section directly into a CPU register or the other way around, or copying something from immediate data into a CPU register. Now that we can access memory via a pointer, there's something that we're going to have to think about. And this instruction shows that off. What does this do? I don't remember what this does. Let's read through it real fast. Oh, it goes through this list of values. So I got a list of signed words. I say that because some of them are negative. And we're going to go through it, and anything that's negative, we're going to set it to 0. We've got a counter up here that keeps up with how many items are in our list. And as we walk through the list, oh, sorry, I apologize. This will just tell us how big our list is. I said that right the first time, I claim. All right, so first, we're going to use the loop instruction. So if count is 0, I mean, I know it's not here, but in general, if it is, then we don't want to take 65,000 iterations. So we'll handle that as a special case. We'll look at what's in count. And if it's 0, we're just going to skip over all of this, because if there's nothing on the list, there's no values to modify. So these two instructions you can think of as getting around the bad behavior from loop if our loop counter starts out at 0. So now if it's 0, we skipped over this. So now we don't have to worry about a counter that's 0. We already took care of that. So just like our previous example, we'll set SI to be the pointer to the start of our list. We'll set CX to be the number of items in our list. So we'll just copy count into that. And then over and over, we'll do these instructions, decrementing CX. So I'm kind of jumping ahead to the loop. So what do? We look at the current item and see if it's 0 or not. If it is bigger than or equal to 0, then we don't have to modify it. So we skip over this next instruction. We jump, if it's greater than or equal to 0, we jump over the next instruction. And here you can see we're just moving our pointer ahead. What is the instruction we skip? Well, that's what we said we were going to do. We zero out the current item. We copy a 0 into whatever item SI is pointing to. Now, really, these two instructions are our problem. It's just a problem we didn't know about yet. The compare instruction can do a 1-byte compare or a 1-word compare. If you're comparing a register against immediate data or a register against memory, then it's obvious which one you want, or it's obvious to the assembler which one you want, because by the name of the register, you can tell how wide it is. But not so here. Here, well, whatever that pointer points to, compared against 0, is that a 1-byte comparison or is it a 1-word comparison? And just based on this one line, the assembler can't tell. The same is true for this move down here. So we have to help the hardware using what's called a data size override. This will make, it'll make our instruction a little bit longer to type in. It still assembles down to something that's just as short. We just have to tell the assembler what to assemble it down to. For this compare, is that a word size compare or a byte size compare? If the assembler can't tell, then we can put word PTR in front of the indirect address. Same thing for the move. And this tells it this is a word size compare. If you needed byte sized, you would have said byte PTR. And this tells it which version of the compare to do, and same for the move. We could have done the same thing with the comparison up at the top. There, the assembler can tell that we wanted a word size compare. We've never had to do that before because, well, count isn't a register. It's a label in our data section. And when we define that label, we said this label points to word sized stuff. You can still put that, but we never needed it there, but we do need it for instructions like this. Questions before I try to move on?
Can you do this for normal variables in the data segment as well? Like if you have a word, but you only want to get like the low order byte of it, can you say like, hey, I know that this is a word. Can you just pretend it's a byte for me for a second?
So I'm going to guess. And I have assumed that you can, but I haven't actually written code that tries to do that. You could always fake your way around it by taking the offset of something in the data section and then you putting that in a register and then doing what we're doing here. But it seems like you shouldn't have to. It seems like this should let you do that. And again, I'm guessing, but I bet you can. Like here, we could have said, oh, even though I said that's a word. And you can't see it. But over here on my slides, I've got a note that says, I hope you can't see it, that says, I think it would work in that case. I should check on that. And I just didn't get around to doing it before class. Good question, though. Maybe someone can try it before the end of class today. All right, any other questions? Here's the slide that I've been predicting. And this is the list of registers that you can do indirect addressing with. BX, we've used that a lot. I mean, we've got AX, BX, CX, and DX as our kind of go-to general purpose registers. And we probably haven't used SI and DI. Remember, those are the source and data index registers, and they all work. And BP, I don't think we've used that at all until now, but it stands for base pointer, and it's normally a pointer into stack memory. In fact, so much so that when you use these registers, the assembler decides which segment you want based on which of these registers you're using. So if you use any of those first three, SI, DI, or BX, unless you say otherwise, it's going to look up those as offsets into the data segment. And if you use BP, it's going to use that as an offset into the stack segment. Questions? And over on the right is just a list of some of these registers, when we first learned these four were in a block together, so they're still listed that way. SP is here, but it's not on the list. Stack pointer. Questions?
Are there any that are used for locations in like the code segment? Like if you wanted to like be weird about it and store the location of like some instruction and use the jump instead of using a label, use something that's inside of a register. I tried that earlier today and it works. So like, what would be the one to use here for that?
Well, there's an answer. It's just not a useful one. So you can use segment override to get to your own code segment. And we learned the syntax for that. It's been 1 or 2 lectures since we saw that. I know it's in your current programming assignment, the tabs assignment. I think it is. Oh yeah, because you need that to get to the command line arguments. The instruction pointer by default accesses stuff in the code segment, but you don't normally, I mean, the instruction pointer is keeping up with the next instruction you're going to run. You wouldn't normally want to try to use it to store something else, because then your program, if you modified it, that would be the next instruction you would run. You can use segment override to get to stuff in your code segment, but none of the registers we would normally use are going to go to the code segment by default. All right, we've really just seen one indirect addressing mode, and that is you can take any of, I'm backing up, you can take any of these 4 registers and you can say, I want you to get what's in the memory location pointed to by that register. There are 4 different ways of doing indirect addressing, and they all have different names, but they're all combinations of the same words. You can either think of them as 4 different modes for indirect addressing, or you can think of one mode that is kind of using all of those features at once. And then the simpler modes are just leaving out some of those features. We'll sneak up on this idea, and hopefully by the time I work through this example, that'll make sense, even if I did a poor job of explaining it there. Let's say you had an array of structs. Let's say you were coming from the C programming language, and you had not just an array of short word-sized values. You had a little array of objects. You had a little array of structs. And pretend this picture shows that. Each of these is one of the structs. They each have multiple fields, let's say. So maybe there's a name field, but maybe the name field isn't right at the start of the struct. Maybe it's 20 bytes into the struct. Maybe there's some other fields that come before it. So the name happens to start partway through the struct. And there's an interval between the structs. So however big an instance of the struct is, that's how far you have to move to get from one instance to the next. Indirect addressing mode, indirect addressing has modes that are made for accessing data like this. Normally, this would depend on you setting up a register to point to the start of, say, this array of structs in memory. And if you had a pointer to the first, and here this picture is drawing this array as if this is the first element, and this is element 1, and this is element 2, and this is element 3. I say that because depending upon what kind of picture you look at, you might assume memory addresses get bigger going down the page or up the page. And I know even in this class, some pictures go one way or the other. Here we're assuming this is the first byte or the start of this array of structs, and addresses get bigger as we go this way. So if SI is pointing to the start of the first instance in memory, and name is 20 bytes after that, then if we could get SI and add 20 to it, that would be the name field of the first record, of the first instance of a struct. There's an indirect addressing mode that'll let us do that. It will let us take the value of a pointer and add a fixed offset to it. So we'll have an indirect addressing mode. We've already seen one that looks like this. There's one that lets us add a fixed offset to it. If we want, and that's fine for accessing fields in just one instance. If the definition of a struct in C tells the compiler what fields you need, and it decides how to lay them out, then using different offsets, we could get to any field in just one struct. But what if we wanted to get to different fields in different instances? Well, if we could have another register that let us pick which struct we wanted, like if every struct was, I'm trying to pick a good example that matches this. Yeah, if I knew what size the struct was, like let's say every instance of a struct is 40 bytes. I'm just looking at what the slide says here. Every one of these is 40 bytes. And let's say I wanted to get to the nth element. So pretend, look, we're in this picture where n is 2. You want to get to a particular element. Well, if you could compute, if you knew where SI was, and you could compute n times the size of the struct, so n times 40, that would give you a pointer to the first thing. And then if you wanted the name field, if you could go 20 bytes past that, that would be the address of the name field in the nth element of this array. There's an indexing mode that makes it easy to compute this. If SI, just like the picture shows, if it's pointing to the start of the whole array, and in BX, I can compute the offset, the number of elements I want to index times the size of the element. If I can put how far, in BX, if I can put how far the start of the element I want is from the start of the whole array, so that'd be n times 40, then I can use a fixed offset of 20 to get to this field. And we've learned all of the instructions we need to do that. The n times 40 part is just a multiply operation. And we've got addressing modes to do these other operations. So to essentially look up any element of this array of structs, and then to look up a field in that. And these are the addressing modes that are going to let us do that. This is the slide. You remember I said a moment ago, you can think of indirect addressing as having 4 different modes. Well, each line of this table shows one of those 4 different modes. But this bottom chunk of the table kind of shows everything you can do in indirect addressing. And all of these simpler modes are just leaving out part of that. So if you can understand this last example, these other 3, even though they have different names, they're all just simplified versions of this last one. So let's talk about this last one. It's called base and index with displacement. The base part is a pointer, and it's got to either be the BX register or the BP register. It's I'll go ahead and say if it's BP, then this is going to index something in the stack segment. If it's BX, it's going to index something in the data segment. This addressing mode, base and index with displacement, can also add in the value of not any register, not just any register, but either DI or SI, these 2 index registers. And again, if it's base pointer, that's going to index into the stack segment. If it's BX, it's going to index into the data segment. So you can add in either of the index registers and a positive or negative constant offset. That's called base index with displacement. All these other modes are really just that with one or more thing left out. My next slides go through these individually, so I'll try and talk through that real fast, but base and index is just this mode without the displacement, without the constant plus or minus n. Base with displacement is, well, base with displacement is just the BX or the BP part with a constant offset, or the index register with a constant offset. So that's why it's called base or index. If you only need one of the registers, you can use either the BX or BP or the index registers. And if you don't even need the displacement, you can also use any of the 4 registers. These next few slides might go by quickly because I kind of said everything that's in this table. So we already knew about these modes. They're called base or index. And again, that's based on the names of these registers. With base or index, you can add a constant offset. I keep saying constant offset because kind of like the example we did before with an offset of 20, whatever you add or subtract to the constant or to the contents of these registers has to be something that the assembler can figure out. It has to be a numeric value that the assembler can figure out while it's assembling your code. And we've got an example of this later. This n can't be a variable, for instance. So you can add or subtract a fixed numeric offset if you want to get a nearby value, as long as nearby is a constant distance forward or backward in memory. If you need a amount forward or backward in memory that you can compute that isn't a constant, well, base and index will do that. You can put a pointer in BX or BP, and then an offset from that pointer in SI or DI. The assembler will, sorry, not the assembler, the processor, when it runs this instruction, it'll add the contents of BX and SI or BP and DI, if that's what you used, and that'll be the memory address it uses, or either of those modes with a fixed numeric offset. So again, like I've probably said a couple of times, this is kind of like the most fancy mode, and these are all just simplified versions of that. I kind of said some of this already. The displacement, the n in plus or minus n is effectively, it's written into the instruction like immediate data. So it's part of the instruction that gets us, or at least what the instruction gets assembled to. So it has to be a constant. It can't be a variable. Yeah, and we already said any of these modes that use BP are going to by default go to the stack segment. If they don't use BP, they're going to go to the data segment. I don't have them highlighted, but we could easily pick them out. That one, BP plus or minus N, BP plus or minus either SI or DI, and these last two modes, BP plus or minus SI or DI, plus or minus a constant. Those would go to the stack segment. So what could we do with these? Being able to compute memory locations as our assembly language program runs, that's going to let us do, it's going to give us some options in implementing things that maybe we didn't have before. Let's say we wanted to implement a square root function, or sorry, actually, sorry, it's sorry, I'm thrown a little bit because there's an error in the table, and I might have accidentally typed that in earlier when I was getting ready for lecture. All right, so let's say we want to compute a square of something. We just have a value, and we want to be able to quickly compute what that value squared is. We could write code to compute that mathematically, and often that's a good way to go. But for a complicated calculation, pre-computing some answers can be a faster way of doing that. We could build a table of squares, and it might look something like this. And this is what made me hesitate before, because most of this table looks okay. 0 squared is 0, 2 squared is 4, 3 squared is 9, 4 squared is 16. I take responsibility for that too. I think when I was getting ready for class, maybe I accidentally typed a 2 while I was looking at this. I also see a 2 down here that might have the same explanation. I'll check that after class. So just pretend this says 1. I think that would make a lot more sense. So here, instead of computing squares, we could just build an array where at index 0, we have whatever 0 squared is. At index 1, we have whatever 1 squared is. So our table, it wouldn't really look like this picture because we wouldn't really have to store the index. That's just for you and I to see. We would just have to store at index 0, a 0, at index 2, a 4, at index 5, a 25. In some cases, if a calculation is tricky, it might be cheaper to pre-compute answers and then just look them up in a table when it was time to compute that. Somebody posted a chat comment. Hopefully it's that the printed slides have that right. So here's an example of so for computing squares, you don't really need, especially for integer squares, you don't really need to build a table to make that computation faster. Maybe square roots, but For squares, you could just use the multiply operator, and that'd probably be faster than a table lookup. But we can come up with an operation where table lookup could be a lot faster. Let's pretend we had an image. Images are a good example because they could have millions of pixels in them. Even if the horizontal and vertical dimensions are not that high, they still could multiply together to give us a lot of pixels or a lot of pixel data. If we just wanted to do something simple, like make the image brighter, now that'd probably be easy to compute. Making an image brighter might just involve adding a value to every pixel. And then making sure it doesn't exceed the maximum value. So if every pixel is a byte of intensity, then we could just add a constant to that and make sure it doesn't exceed the maximum byte value, 255. That'd be easy to write code for, but something like increasing the contrast could be a trickier computation. The idea of increasing the contrast is we want to kind of spread out the range of values. So pixels that are kind of dark, we want to make darker. Pixels that are kind of bright, we might want to make brighter, but otherwise we want to keep the same relative relationship between intensity values. Over here on the right is a formula that we could use to increase the contrast. If we know the range of pixel values from old low to old high, that being the minimum and maximum intensity values in our original image, and we wanted to stretch those out to a new high and low value, then this computation would let us do that. To talk through it, I mean, I won't talk through it in detail, but if this is your old pixel value, if you figure out how far that is from the minimum, divided by how far that is, the highest value is from the minimum. So how does that compare in your range of values? And then you scale that up to the new range of values you want, and then add that to your new low value, then that would stretch out the range of intensity values to give you more contrast on the image. But if you had to do this for every pixel in an image, that could be expensive, especially if you had a giant image. I mean, this is probably unrealistic for images that you and I might normally use, but if you had a 64,000 by 64,000 image, that's 4 billion pixels that you would have to do this computation on, which could take a while. But across those 4 billion pixels, there are really only 256 possible intensity values. That's a lot of pixels, but if you looked at them, you would really just see the same 256 intensity levels over and over, at least they'd get reused. So if we pre-computed how to rescale the contrast for every possible pixel value, we would only need 256 different values. And then for all 4 billion pixels in our giant image, we could just look that up in a table. So here, implementing table lookup could be a lot faster. So we could build a table that had an entry for every original pixel value. And at pixel or at entry, say 100, it could store the new intensity for a pixel that started out with an intensity value of 100. So if 100 was a little bit dark, the increased contrast image could have a 50 instead, so that'd be even darker. A medium pixel like 150 could stay at the same intensity. A kind of bright pixel like 200 could get even brighter. And then once we filled in this table, we could just do table lookup over and over again. If we had this table filled in, what would it take to do table lookup? Well, that would be a good job for indirect addressing. It would also be a good job for that translate instruction that we learned last time. Translate was kind of nice because it let us do some of the same things that we can do through indirect addressing. They're all just built into the instruction. indirect addressing will let us do a lot more things if we can do those kinds of operations ourselves. So let's pretend table was stored in our data section. And let's say we look up the starting address of table, or we get the assembler to tell us that, and we store that in SI. So SI is like a pointer to the start of our table. And let's say we've got a pixel value that's stored in whatever inpix is, and we want to go look up what's in that pixel and rescale it based on what's in this table. Well, we could go get the intensity of that pixel and copy it to BL. That's the low part of the B register. And then we could use an indirect addressing mode to say, and my picture doesn't show this, but you could imagine SI pointing to the start of this table. And then you want to add BL to that. And that would, if every entry of the table was 1 byte, that would index into the line of the table based on the intensity of the pixel. And we could just copy that into the new intensity of the pixel. And this would work, except this would use indirect addressing to do the same thing the translate instruction does, except BL wasn't on our list of registers we could use. It's half of a register that we can use, but remember, it was BP, BX, SI, and DI. So if we want to use B, it's got to be the whole BX register. Well, we only need a byte, but indirect addressing uses the whole BX register. So if we want to take a 1 byte pixel and use it as part of an addressing mode, we've just got to make sure the high part of BX starts out with a 0 in it. So this seems like a way we could use indirect addressing kind of to simulate what the translate instruction already does for us. I clear out all of BX, and then for each pixel, I copy the intensity of that into just the low part of BX. And then I take start of the table plus BX, which is, the high part of it's going to be 0. So just the low byte is going to determine which entry of the table I want. And then if I look up line 100 in the table, that's going to give me the content, the rescaled intensity, the contents of the table at line 100. And I'm trying to think what this line is telling us. You can do a lot of neat things with indirect addressing modes, just like in C class, being willing to use pointers instead of just directly working with the contents of memory. Well, it can make our code more complicated, but it can also let us solve problems that would have been harder to solve otherwise. We got a couple more tricks we can do with indirect addressing modes. And one of them is to implement what we would call a jump table. Now, we talked about this, or you talked about this in C class, when we talked about the implementation of the switch in C. And we said, well, the plan for switch in C is it ought to be something that can be implemented as a jump table. What does switch do? Well, it lets you have a value that you can compare against a bunch of constant values, and then it picks a block of code to execute based on which value or which value it's equal to. If we had to, we could implement this with a bunch of comparisons. If you had to implement a switch, you could write an if statement that compares the value in the switch. And when I say switch, I mean switch statement from Java or from C. You've got a value, you're going to pick a block of code based on that value. The reason that statement exists is because it's something that can be really efficiently implemented with a jump table. And in assembly language, we can build our own jump table. We have access to code at that level. What does it take to build a jump table? Well, we need to just take the the locations of different instructions in our program. And we need to turn that into data that we can compute with. And that's what's going on here. This looks kind of weird. It looks maybe a little bit backward because up here in my data section, I'm referring to labels down here in my code section. And you can do that. I've got in my code section, I've got a label. This looks like a 10, but it's L0. So think of this as label 0, label 1, label 2. And those labels assemble down to the location in the code section where the next instruction is. When you jump to a label, you're really saying jump to whatever location that label evaluates to. So the label kind of marks the start of a little section of your code. Up in your data section, you can use the value of labels to initialize different parts of your data section. So this TBL says, make me reserve 3 words in the data section of my program, and let the first one be whatever label 0 is, whatever index it is in the code section. Same thing for the next word, let it be label 1, let the next one be label 2. So when the assembler writes out this data section, it's having to look ahead and say, oh, where does this label end up being in the code section? Where does this next one end up being? But the assembler can take care of all of that. And once it has built code to initialize our data section, the next 3 words here will actually have locations in the code segment. They'll be initialized to locations in the code segment. Really, they'll be the offset of each of these labels in the code section. Well, this is like an array of pointers to different locations in our program, and we could use that array to jump to different locations in our program. We just need to decide which one we want to jump to. Let's say that we got from the user some input. Like, let's say the user was going to enter the number 1 or 2 or 3 or 0. So they're going to enter a number. And then we're going to use that to jump to one of these 3 blocks of code. Well, we could call, if we want to read a key typed in by the user, we could call the system call to do that. So system call 8 will read a key from the user. So these first 2 lines get a key typed by the user. That's going to be an ASCII code for a key, which means it's going to be hexadecimal 30 for if they type a 0, 31 if they type a 1. And they laid out the ASCII character codes so that if you just look at the low part of that number, it will tell you the numeric value of what they typed. We haven't really, I don't think we've really seen this instruction yet, but there's an AND instruction that you can use to mask off certain bits at the assembly language level. So if we take whatever's in AL and we AND it, well, when we read a code from the user, of course, it's going to be in AL. If we AND with 0003, well, that's hexadecimal, but if you think of that in binary, it's a bunch of zeros with 2 1s in the low order bit. ANDing with that, just like in C class, it'll discard all the high order bits, it'll set them all to 0, and it'll just leave you with the 2 low order bits. So it'll be the low order bits of whatever ASCII code we got back from this read. If the user typed a 0, well, all we'll be left with here is a 0. If they typed a 1, we'll have a 1. If they typed a 2, we'll have a 2. We can look up which block of code we want to jump to in this table by taking what's in AX. If AX is a 0, let's pretend we want the first element of the table. If it's a 1, we want the next element. We can't use what's in AX as an offset into the table directly, Well, because every element in this table is 2 bytes. So before we use it as an offset, we need to double it. Well, doubling stuff is easy. We just have to add it to itself. So that's what this next line does. We're doubling what's in AX. And then we'd like to use AX as an offset from the start of the table, but we can't do that with AX. Remember, our 4 registers we can use with indirect addressing are BX, BP, SI, and DI. So if we want to use this as an offset into the table, we've got to copy it into one of those registers. So that's what we do next. We copy our doubled value of AX into BX, and then we can use this as an offset into the table. So this assembles down to the start of the table plus whatever's in BX. Now, and then if we use that as the target of our jump, it'll go get whatever's in this table, and it'll set that as the new instruction pointer. And if the offset gives us L0, that's where we'll jump to right after this. If it gives us L1, that's where we'll jump to right after this. This is the first time we've used something besides just a literal label as a target for a jump. But a jump can take a indirect addressing mode, just like other instructions that we're using. So if, say, AX, like the picture shows, if it happened to be a 2, when we do this index, it's going to get 2 elements into this array, so whatever L2 assembles down to. And then when we do that jump, we'll jump straight to L2. I lied to you a little bit. I did it on purpose, but it was when I was describing this instruction here. If you look at this, or really this address here, if you look at it, it's really backward from what we talked about. That doesn't matter to the assembler, but we never said you could use a variable and then index from that. And you can't. This mode is really BX plus a constant offset. I won't rewind all the way in the slides, but the mode I'm really using here, even though I didn't write it this way, is BX plus or minus N. Base plus or minus offset. Here we just put the constant offset first, and we put the register that I'm offsetting from second. And that's fine. The assembler can take that. You don't have to write them in a particular way. But notice when I use a label from the data section like this, I'm not getting the contents of that label. I'm getting the offset of that label in the data section. And then I'm saying, all right, go this many bytes further into the data section, and then jump to whatever word is there, or jump to the, go get the contents of that word and then jump to that location. The reason I'm making a big deal about this is, and this is some of the stuff that I was saying before, TBL, I'm not getting the contents of that variable. It's being treated as a fixed offset. It's the N in the BX plus N. I just wrote the constant part first and the register second. And like I started to say, the reason I'm making a big deal out of this is it's easy to get confused about that. Since you can refer to variables as part of an indirect address, it would be easy to write code like this. This code doesn't work, but let me first tell you what it's trying to do, and then I'll say why it doesn't work and we'll fix it. So up here, I've got a list. It's got room for 10 elements. I don't care what are in the elements, 10 elements, each of type, each byte sized. I got a variable N that let's pretend is an index into this list. So right now we're starting out at 0, but let's pretend I could use it to refer to the first element 1 or element 2 or whatever you want. What's to keep me from writing code like this? So let's say I'm going to use AL to add up a bunch of values. I start AL out at 0. I load into SI the offset of the list. So if you think of this as a list of 10 elements, SI is pointing to the first one of those. But let's say I don't want to get the first one. I want to get the nth one. Can I say take SI plus whatever's in N? Well, this will assemble. It just won't do what I just said. The part that I said was wrong, the part that I said that was wrong was SI plus whatever's in N. This assembles, but that's not what it does. It's going to be SI plus whatever offset N has, the contents of N. Like if N had a 0 in it or a 1 or a 2, isn't going to have any effect on this instruction. It's going to treat N as a fixed offset into the data section, and it's going to add SI to that, which isn't going to give you the value of N. Question?
Yeah. On the last slide with
The previous slide?
Yes.
Yes.
Yeah. This one right here. This jump instruction right there. I noticed that there are square brackets around TBL plus BX. Do you want that in this case? Because what's you're saying, you're not saying find something, you're not saying take the piece of data that this points to and jump to that, because that wouldn't make any sense. What you
It
want.
would. That is what you want. Let me finish this, because this doesn't. So I got one more slide after this.
Wait, yeah, yeah. So yeah, okay, sorry.
Because I claim I'm on a roll on this. So I'll finish this. Here's how to fix it. And then we'll go back and answer that question. All right, so this doesn't work. And the reason it doesn't work is because, well, the square brackets, if they were just around N, they would say, give me what's at N's location in memory. But they're around SI plus N, which is saying, take N's location in memory, add SI to that, which is another offset. I'm not sure that's a useful thing to compute. It'll ascend, I mean, you can compile it. It just probably won't do what you want. So take N's location plus whatever's in SI, and then look up what's at that location in memory. It's just, that's probably not going to be anything on this list. What if you wanted to use N as an index into this list? That's going to take help from another register. So if you want to go get N and treat it as an index, you're going to have to copy it to a register that can do that. And that's what I'm doing here. Instead of this piece of code that doesn't work, you can say, all right, go get what's in N, copy that to BX, and then you can add BX to SI, and that works just fine. SI, we already made it a pointer to the start of the list. Now BX had whatever N contains. So if N contains a 3, this will look up element number 3 on that list. You just had to copy it to a register before that would work. That's all the new material I'd hope to cover. So we're done. We had a question a moment ago, which may have been answered. There was a question about whether we need the square brackets around that. Let me address that, even if the person asking it decided that we do need these. And I think we need these. The reason we need them is when I say take TBL plus BX. Well, TBL is the start of this array in memory. So TBL is like pointing at that L0, pointing at the word that contains L0, because these are just the initialization values for these 3 words. So the first one's going to contain L0, the next one's going to contain L1. And when I say it contains L1, if you looked in that word, it would contain whatever the address of the instruction after this L1 is. So you're saying take wherever TBL starts in memory plus whatever index I just got from the user, and then go get the contents of that memory. Well, so let's say bx is 4, like it says in the explanation of the example. So take TBL, go 4 bytes later in memory. TBL is pointing to the start of this L0. 2 bytes later would be this L1. 2 more bytes later would be this L2. And again, like I tried to say a moment ago, the L2 is what's in that byte. So the square brackets say go get what's in that byte and then jump to that. Well, the L2 is what this, sorry, I said whatever's in that byte. I should have said whatever's in that word. Go get whatever's in that element and jump to that. Well, L2 is what's in that element, so that'll jump down to whatever comes after L2. I've used all my time for today, but we got through everything with a little explanation on this. Any more questions before we call it a day? I'll stay around after class if anyone has questions. All right, I'm not hearing any. Go ahead.
Yeah, I had a question.
Sure.
Can the indirect addressing be used with the conditional jump instructions?
I'm not sure. I feel bad because I haven't tried that yet. The reason I hesitate on that is the jump instruction can jump to anywhere in memory, but remember the conditional jumps have a restricted range, which means they use a different way of coming up with their destination. Because of that, I'm suspicious that they can't take an arbitrary address as their destination, but I haven't actually tried it. I'm going to go out on a limb and say, I bet they can't. I'll try it right after class and I'll publish an apology if I'm wrong about that. Someone else said something?
I tried it earlier today. It doesn't work.
Woohoo! So I claim I'm right with support from a student on that. So I'll try it again anyway, but that makes sense that it wouldn't be able to do that. Other questions? All right, thanks for your attention. Let's call it a day. Remember, your next program is due on Wednesday. Good luck on that. I'm trying to keep up with Piazza, so if you have questions, that or office hours are a good place to ask them. I'm still recording, so I'll stop that, and I'll see you on Wednesday.